On behalf of Lambda Lunch and together with Michal's Erlang Solutions, I'm very glad to have you here, Garrett. And without much ado, I'll just say that real highlight of your persona for me was done by Michal when he heard that you contacted us at the Lambda Lunch. So, Michal, why don't you say a few words, because to be honest, you deserve the honor.
No, thank you very much for having us here. We are very proud to host the Lambda Lunch for the first time. And indeed, Grant is well known within the Erlang community, but actually the purpose of this meeting and other stuff will be to send the message out from the Erlang community. So please listen carefully, and it's great to have you all here.
So the real purpose is actually afterwards, so that you all are part of the Erlang community. Is that okay?
Go for it.
Yeah. You're going to find, like, shortly into this, that I'm a religious fanatic. This, like, Erlang stuff. It's actually not Erlang, it's more general than that, but it's absolutely religious fanaticism. Okay. So first of all, thank you very much. This is great. I mean, I came here thought, well, it would be kind of cool to have an opportunity to present to the functional programming group, and it's turned into a bit bigger event, and I'm honored and humbled. So this is my first time in Poland, and somebody asked me what I knew about Poland, and I'm like, okay, point taken. So I bought some books, and I'm reading the history, some histories of Poland, and it's like, okay, not only did I not know it, I now know that I didn't know anything. This is an absolutely fantastic story and history, and I'm skimming through because I want to get through it quickly. I'm going to go back and I mean, I don't know. My quick take is, and I'm not here just to like blow smoke. Like, this is like the most amazing hero story. The nation of Poland is unbelievable. So I'm really excited to try to correct my embarrassing ignorance of Poland. And it's a great pleasure. So it's a pleasure to be here as well. So I'm going to be talking about reliability features of Erlang. And as I alluded to, this is a little bit more of a religious topic for me. And I'm notorious for like coming up with titles that are politically acceptable and then changing everything. Like, I brought up some bait and switch. So it's like, oh yeah, reliability features of Erlang, that sounds good, and it's going to be on something completely different. It won't be, don't worry. Okay, so let me start out by saying, like, as I'm presenting to a group of presumably functional programmers, let's do a survey. Well, let's not presume. Who would consider themselves tool of choice, weapon of choice from a programming language, a functional language? Okay, about half. Who would say an imperative language? What, vector? Like vector array language? So that we didn't get everyone voting there. So what's something in between? HTML and CSS could be. Okay, that's fine. We'll go with it. We'll go with whatever is out there. We'll accept that. So I don't want to pretend like I'm some hardcore functional person. So my confession is, I spent some time at University of Edinburgh in the university, and I was in the AI department. And I was in the AI department for 2 weeks. And the reason I left was they used ML it was of course created at University of Edinburgh. They used ML in the AI department. And I was competing with students who really sort of had this functional thing figured out. And so you'd have like 3 lines of recursive code that navigated this maze. And I'm just like, what? I mean, I might as well be reading like just binary or K or some really cryptic thing. I was like, there's no way. Everyone else seemed to get it, but I didn't get it. So like, I'm not going to get an F. I'm just going to quit. So I quit and I moved into the CS department where they used C and Pascal and things that I could sort of understand. So I didn't have to like look at 3 lines of code and go, why, how, like this is like some sort of existential experience. I could just say X equals 1, 4, like I could just hack stuff and like every little step made sense. So I'm kind of an imperative guy by heart. My career has been spent in languages like C, C++, Java, Python, Bash. I mean, just languages that you can just hack the living crap out of things and get things to work, and that seemed fine to me. So really, that's kind of my disposition. Now, truth is, I've changed. I have been changed, but I don't want you to think that I'm some hardcore functional person. So my experience was really primarily imperative. A lot of 10 years in Java. Did a lot of client stuff. I worked for InstallShield, if you've known InstallShield. also the multi-platform installation. So like, complex client-side code. And I got about 5 years ago, so this is fairly recent, into server-side stuff and platform as a service. So I worked for a company called Stacks when it was first started, and that has since been bundled up into a company called CloudBees. That's the company that I currently work for. And we set out in Stacks to build a platform as a service. And so a platform as a service is basically you take code as a programmer, give it to us, and we'll make it run in a nice operational scaled environment. And we focused on Java. If you're a Java developer, give us some Java code, we'll take it, push it to the cloud, and run it. We'll scale it up, scale it down, give database connectivity, monitor that things break, we'll fix it. So basically no operational requirements, just give us code. So in my purview as a software programmer, I went from like building software. So here's a program. I'm gonna have a code base, compile, artifact, program, to a system. We originally started to try to make the system a program. Like we could just say, here's my program, here's the cloud, it's my program. In fact, some people do that with like Chef and other things. And got to the point where I realized that this is impossible to keep up with. The system started to evolve out of my control, and I gave up completely on the idea of being a programmer, writing a single program, here's my program, blah, 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 ship it, to like a systems person thinking, this does this, this does this, this does this, this does this. And that's kind of in this area of DevOps. Is DevOps a fairly common term out in everybody? I don't mean to ask a dumb question. I don't like the word DevOps because it's just like, oh, we'll invent a new word for like system administration that's done correctly or smartly. But this was in the area of DevOps. So it's like programmer mindset, highly leveraged code bases, but applied to operations and system. So this is sort of my realm, my transition from sort of traditional programming to now like sort of sysadmin DevOps space. So in this whole paradigm, like this environment of cloud, servers, operations, the topic of reliability started to become central. So we had two people, literally two people, and the theory was that two people could just run a company and we could have thousands or tens of thousands of customers. So to do that, you have to have systems that aren't breaking all the time. Because if they're breaking all the time, two people are always fixing them. So they should just work. So if you put something out there, it should just work. It should be zero to very, very, very low maintenance. Otherwise, you can't do this. You can't have a very small company and a large customer base. So this was a problem, it was a continual problem, and I experimented with all sorts of different things, and really at the time Python was my weapon of choice. That was my sort of preferential language. Python is just like ruthlessly pragmatic, direct, like just I want to get this done. I don't want to think about language design, because if you know Python, it's not like I guess if like utilitarian and raw is like beautiful, then you love the beauty of Python. So we did this, and I had Python all over the place. We were using AMQP for message passing, RabbitMQ, actually Qubit originally, and then RabbitMQ, and we had this really nice distributed system, and ran into this particular problem. I call this the monitor problem. It's actually the Stacks monitor problem. So in this environment, the goal was to run people's software. So you give me your software, I'll run it. To run that effectively, I need to monitor it. So I need to know when it's using too much memory or too much I/O or whatever. Thousands of different metrics to pick. And we wanted to create a feature set around this problem of monitoring. So give you, the developer, the ability to react to different situations, different metrics, different changes, etc. So this becomes a really challenging and interesting problem when you have thousands or tens of thousands of applications. Because if you have thousands of applications, you have tens or hundreds of thousands of data points landing, or even millions of data points landing within your collection or monitoring scheme. So I took this on and I used Python. Python's great, so I just did it. And put it in production, and it would run for about 6 or 7 hours, and then it would just completely freeze, completely lock up. So has anyone ever run software that just sort of mysteriously locks up, just stops? So a few heads nodding. So you're in a systems or an operational environment. You're dealing with infinity. You're dealing with like, if something can possibly happen, it will absolutely happen. It's just a matter of time. So this one gave us about 6 hours of piece, 6 hours of function of operation. And it hit around 300 megabytes of residential RAM, maybe 600, and then boom, dead. The process lived, but there was no CPU activity, there was no I/O activity. It was basically comatose. And of course, this is symptomatic of deadlock. You know, threaded environment. You get things that are contending, and the Python is notorious for having this GIL, which is a global interpreter lock, which is sensitive to threading and locking issues. I knew I was running into a really difficult problem here. And so we're using MQP, and MQP is a multiplexing protocol. So you can have multiple connections running on a single, virtual connections running on a single connection. Really complicated protocol, and all the client libraries are really complicated. And I went through literally every single Python library to try to figure out how on earth we could get this thing to stop deadlocking. That was one path. The other path was let's open it up and try to fix it. So let's go see like where is the deadlock happening and where, and it's like, okay, here's a problem. If you ever like fix your problem by generating 10 other problems, or that like the first problem just becomes utterly eclipsed by the others, that's what dealing with like threading difficulties will give you. If you have a threading problem, who's dealt with threading problems? Not just lockups, but just threading problems in general. Has anyone found it really good? Is anyone happy? Like, is anyone now sitting in this room feeling joyful as a result of, oh yeah, I figured it out. I did. I broke through the barrier. It's just a barrier, you have to push through it. Anyone? No, you don't. You're dead. You hit that problem, you're dead. So I tried to fix that directly. The other solution is just to like select all, like Control A, select all, delete. So change everything. So I knew that there was a product out there, a technology out there that took a fundamentally different approach to concurrency. There were no threads, there was no shared memory. There's no threading problem, there's no locking problem, there's no mutexes, there's no dealing with this because Erlang pays a huge price in performance by copying things all over the place. So that big performance penalty is made up for the fact that there's no shared memory. I knew this was a shared memory problem, this is a locking problem, this is a tension problem. And I knew that at least I wouldn't have this issue with Erlang. I also suspected that in Erlang, as a concurrency-oriented language, that the community wouldn't write terrible, like concurrent code, the way I was running into. And it turns out, though, fast forward, it turns out that's actually generally true. The Erlang community is generally pretty darn good at dealing with concurrency problems. But that was more of a guess at that point, so I didn't know. All right, so I did this thing and scripted all of it. Select all, delete, rewrote it in a very focused way and solved the problem. So we got our monitoring, we got our really extremely fine-grained monitoring, where we were monitoring tens of thousands, even hundreds of thousands of things concurrently. Pretty sophisticated even today. This is 5 years ago, so pretty pleased with that. But the process there showed me what I thought was a better way to build software, build systems that had to run a long time. This topic of reliability sort of hit me full force. Like, this isn't just a matter of getting something to work. This is a matter of like having a concerted strategy for like succeeding. Right? The monitor prior to this was fail, pound fail. Right? Twitter, monitor fail. You failed. You can't run something for 6 hours and then have it stop. Because this is basically a window. You basically have a rolling window problem. So you have like megabytes or gigabytes even of residential RAM. If that thing freezes and you have to kill that process, you lose all the state. It was terrible. It was a disaster. So Erlang solved this and then informed me of different ways and different topics and different concepts and things that I'd never thought about before. So that's sort of what we're going to be talking about. So before I get into the details of Erlang and reliability features, something interesting here. So we got acquired or rolled up into CloudBees. And when CloudBees did their due diligence, they looked at this code and they said, "Oh, you seem to use a lot of Erlang." I said, "Yeah, it works pretty well, and it works pretty well." And they said, "Well, that's great. It's kind of a weird language, And I got sort of the impression that possibly there was a desire to maybe refactor this and maybe move Erlang out as a strategic platform. This is very strategic in our environment. So that's nice. I can appreciate the goal of the company to try to avoid technically risky or risky technology. So you take a technology on, and if you can't find developers to support it, then it becomes a risk. If you can't fix bugs because the one guy or the two guys, three guys are those individuals are no longer available, you're kind of dead. So there is a very legitimate strategic bet on technology that companies make all the time. And Erlang sort of smells funny and looks funny to most companies. You have to sort of be committed to the merit of a solution. And a lot of times companies are. CloudBees is very committed to the merit. So as it turns out, this software stayed. Why? Because it worked. It worked very, very well. There was no maintenance. You know, no one's going in there and fixing things. And it's like one of those adages, if it's not broke, don't fix it. It goes a little bit beyond that, though. And so, hang on a minute. I missed a slide. Sorry, reordering problem here. I want to redefine reliability for a moment. I don't want to redefine it, but I want to introduce another concept. So reliability is one of these terms that sort of bothers me. It's like performance. You see in the videos, like, you know, performance, something goes fast, it's good. Something goes slow, it's bad. Something's reliable, it's good. Something's high quality. It's like saying something's great. Oh, that's great, yes. We want reliable software, we want fast software, we want, you know, performance. It's like saying we want things that are be good and happy. Completely agree. We all want things to be good and happy. But as engineers, we would like to be more precise about our thinking here. And it's difficult when we talk about reliability or quality or any of this thing to be concrete. Everyone wants it, but it's difficult to talk about it. So I like to have something that's in between. I like to have a kind of a fuzzy concept that we can actually measure and reason about more specifically, more pointedly than reliability. And that's, for me, survivability. So I like to think of successful software as software that is running. Right? And I use evolution as a model for that. So successful organisms are organisms that exist. Look at the coelacanth. The coelacanth is like a 250 million year old design. It's not a very attractive fish. Basically, truly a living fossil. We usually find these things fossilized, but they're actually living. So we can say, well, this is kind of a crappy old design, but it isn't. It's a brilliant design. It's running. It's survived. It exists. So to me, the measurement of great software is that it exists. It's running someplace. And it's very closely related to reliability, because software that breaks, fails, is selected out of the gene pool. Right? We gradually remove it. But you'll hear me talk about survivability a lot, so I'm going to throw that in here, because I think it's a slightly more precise term, even though it's ambiguous, even though it's slightly like abstract. It's like, if you can get something to live and live in the face of competition, you're doing well. Because there's other stuff out there that will eat your software. And I think of it as like, if my software's running, that's sort of currency for me. If none of my software's running in the world, it's kind of like I have less currency as a professional, as a programmer. So it's that survivability topic. All right, so with that context, let's talk about the one thing that I'm going to really talk about. This whole talk about reliability centers on process isolation. That's it. I can stop right now, right? Drop the mic, badass, MC, off the stage. Process isolation. Everyone like, yeah, process isolation. All right, so we'll actually explain what this means. Don't worry, don't worry. Okay, who here has ever used like Windows 3.1? All right, great. I thought I was going to be like the guy that, yeah, it's an old timer who used Windows 3.1. No, I remember. So Windows 3.1. I may be wrong on the. I'm pretty sure I'm right about this. So this is like preemptive multitasking. This is cooperative multitasking. So Windows, at a particular point in time, was just a program that ran on top of DOS. It's a graphical program. So like one program. And then it would host other programs. So you could run other programs with it. And then those programs would have to cooperate and yield time. Right? So there's no preemptive multitasking. There's no kernel. There's no user space. There's no separation. So what you had is like this happy environment where everyone got along until somebody decided to not get along. And this could happen innocuously and innocently. You just have a bug in some code and you start to corrupt something. Right? Who knows what happened there? It's some unexpected state. Something has changed. Some bad thing has happened. The universe knows, but you don't know. But at some point, inevitably, we go to the time to reboot stage. Now, if you have Windows today, you know about rebooting. This was like rebooting every few hours. Like today, if you can go a few days without rebooting Windows, that's awesome. That's like an epic uptime. But there was a time when Windows was much worse. That's like an old operating system. It's not even an operating system. It's like a disk operating system. We're just going to like run a graphical environment on top of that. So that's not an OS. Today's modern OS looks like this. They all look the same. It's not even modern. This is like the way that things, Windows just skipped. Windows, like Microsoft or something, just said, we're not going to do an operating system, we're just going to like be opportunistic here. They did pretty well for themselves and some people. But operating systems look like this. It has a kernel and it has isolation. So every process is in its own space. There's no shared memory across processes. And so every smiley face there, perfectly happy, running kernel services. Kernel services provide memory management and access to hardware layers, interrupts, other core services. So the idea of a kernel is that it's small, it's focused, it's reliable, it shouldn't fail. If the kernel fails, it's game over. So the kernel should be reliable. It should be minimalistic. It should do very, very few things, but do them extremely well. User space is where you can do fancy things. So in user space, if something goes wrong, it's also happy. There really is no bad state in a well-designed operating system. In fact, a well-designed operating system assumes that there's going to be a failure. Of course, if we're dealing with infinity, at some point, if it can't happen, it will happen. So there's an operating system and this type of system environment. This is perfectly acceptable. So who uses Chromium? Chromium or Chrome, whatever. It's great because every tab has its own OS process. So if you get into an unhappy state like this, whereas like in another program, your entire browser would have to be shut down. You can just go kill 9 the one tab that's bad. And so it's, maybe I shouldn't say also happy state, it's like fine, whatever. This is fine, this is what we run. Everyone today is completely accustomed to this type of environment. Every single laptop, frankly, every single phone, probably if you're running Android or iOS, has this, I don't know, does iOS have a kernel? It must. Yeah, so Android is running Linux, so I know what that is. We're so used to that. All right, so name a single environment. So that's the operating system. So I'm going to apply this to programming. Name a single program, a single application environment that does this, that does kernel and user space separation. Name one. Can you name one? They're all Windows 3.1. They're all running the same heap. They're all running this. Right, this dichotomy here. They're all running this. I get a little corruption in one of my threads or one of my processes, and all goes to hell, and your whole process goes down. Of course, the one that does this is Erlang. The designers of Erlang came out of this environment where concurrency was an extreme problem. You're dealing with a telecom switch, dealing with tens of thousands of concurrent connections. If one connection goes bad, you can't bring the whole thing down. And this was back in the 60s. So there's never a question as to how to design a language that would run telecom switches, communication switches. It was always going to be something that had a kernel of focused, shared services, and then isolated processes. So the first and most important thing when you look at Erlang is process isolation. It's consistent with every operating system that you touch today, probably. Most, not every. I like to use extremes. It's religion. 99.1. 3 nines. So it is particularly enlightening. And it took me a while to sort of this light bulb to go on saying, okay, the designers of this application this technology wanted it to resemble the feature set of an operating system. So one of the things you can look at is Erlang is an operating system for your code. And that translates into some very interesting things. So if you get isolation, you automatically have a system. So here we have black boxes. So we don't know what they do. Don't care. We care what they do, but we don't care how they're implemented. We don't care what's inside. And we have exchanges between the black boxes. So these are processes that are isolated. They don't share memory, but they have to communicate over message passing. If you have isolation, the only way to build anything is by way of a system. So this is like an automatic next conclusion. You say isolation, you're talking about a system. Now, when you have a system of isolated components that are talking by way of message exchange, you can deal with a failure in isolation. It's isolated, right? So the failure is isolated. Get it? Isolation? See that? See where I'm going with this thing? So isolated, it doesn't affect the other things. Now there's an outage here, right? We can no longer communicate. But these other systems are running fine. These other components of the system are running fine. They don't have the service available, but that's common. Imagine, for example, let's say that this was Nginx. This is an app server. This is Memcache, and this is a database. Your database, like even in administrative capacity, you should be able to turn a database off for a second or two and have your application running. Right? So your application is out, fine. There's all sorts of other things that can go on and services that can be provided while that database is out. That's a system. So now we're starting to talk about system and bringing it into the area of your code. Not a DevOps, not a sysadmin, but the code that you run and you architect. I'll show you a very precise example of this. So we're going to get to code network. It's not all religious dogma. But so you have failure, and then what? Once you have failure, you can have a restart. So this is recovery. This is how we get back to our state. Every system, any complex system that you deal with today does this. So it's not like this is like an invention of some new bold vision. It all works this way. So we used an example of a database. Well, think about another example. I'll use a bit of a profane, not profane, but a bit of an emotional example. A friend of mine was born with a heart condition that caused his heart to grow faster than normal, which gave him an expected life expectancy of about 35 years. When he hit that, this literally happened. He had a heart transplant, right? So he hit that point. His heart got too big. They literally took his heart out. I mean, I know this happens all the time, but it's just like incredible to me. His heart out of his body and put another one in and connected it and gave him a bunch of drugs, and then it restarted. Right? You can't do that like with the brain stem yet. That'd be awesome if we could do that. Right? But the heart is one of those units that is isolated enough so that this can actually happen. So let's take another lesson. Sorry about that. This just occurred to me. So religious and science and a little bit of bizarreness. Let's bring it back to technology. We are all, some of us are connected to a network. This is connected to a network. There's a phone here. She's connected to a network. So there's a wireless access point someplace. Who has had wireless access point problems in their life? It's like something you go to a counselor for. You go to a therapist because you have wireless access point problems. Should be an acronym for that. Right? So that's a network of independent, isolated systems. Laptop, wireless access point. Maybe there's a peer network. What access point goes hooey? What do you do? What's the known solution? What's the South Park solution? It's to fix the internet. Yes. You pull out the plug, you wait 3 seconds, you pull it back in, you've got your network restored. Right? So I'm trying to make the point that this is not crazy or innovative or even interesting. This should be so fundamental to our thinking about reality that it's just the way we do things everywhere at every point. The sad thing from my point of view is that most application environments don't act like this. They don't give you the tools, they don't give you the semantics, they don't give you the runtime characteristics to do any of this stuff. But you have to do this at the operating system level, which is fine. But we're talking about Erlang today. Okay, so this is really, this is like, I should just pick 10 more examples. Just go ad nauseum and let it go. You get it. This is the centerpiece of everything. All right. So once you have something that can be recovered, it introduces a completely different way of dealing with problems. So most code deals with problems through, I should say most, a lot of code deals with problems through what I would call defensive mechanisms. So you try to guard against conditions that you don't want, and you try to deal with conditions that you don't want. In Erlang, and frankly, good systems design, you don't want to even think that way. If there's a condition that you're not interested in explicitly handling, that you don't know that you can handle exactly correctly, what you can do is allow yourself to fail. Let's say I'm playing God in this situation, and I have a system, and I have a question about this process here. Right? This guy looks unhappy, his state might be corrupt. Remember that Windows 3.1 scenario where one got corrupt and it all leaked through? Well, this is the one, but we're not really sure. What we can do in a system like that, because we can fail and recover, is we can just kill him off right away. Right? So we get to this point, dead, restart. Right? So it changes our entire approach to quality, or reliability, or error handling. All right, here's some code. In Erlang circles, you'll hear this term, let it crash. This is a concrete example of language syntax that gives you fail-fast behavior. So let's go through this. So the first case is, I wanted to actually get some Erlang syntax in here because religious dogma is interesting and all, but the code is also interesting. So OKDB is a tuple. OK is an atom. It's used by convention to tag things. So an atom is like a number, right? It's unique. So OK and OK2 are different. Think of it as 1 and 2. It doesn't matter. It's a numeration. It's a symbol. That's all it is. By convention in Erlang, OK means good. Something is acceptable. It's shorter than good. I would like to change the language and just use different conventions like awesome, awesome, and terrible, sad, result. Okay, so if, for example, connect returns something that we don't want, something that's bad, the convention is to return the tuple error and the error message. So you'll see this very often. Basically, this is saying I'm asserting that this should always succeed. It's like an assertion in any other language, but it's built into the what do you call this? The pattern matching or truth seeking operations equal sign. These operations will bind. So if the shape of this matches this, it matches. So it returns OK, comma something. DB will be bound to that value. Right? So if it isn't bound, it'll fail. So what I'm saying as a programmer here is I always expect this to succeed. So the reason that you see this all the time in Erlang is that whole idea of, hey, everything is isolated. So if everything is isolated out of the system. If I have a system, I can monitor a component for a failure. If that component fails, I'll restart it. Right? And the magic of like a restart is that whole magic of pulling out the plug of your wireless access point. What happens there? Well, I mean, why does that always work? I had a problem with my car a little while ago. Like, there's a brake light. I'm like, I wonder if I just go pull over and turn it off and turn it on, if we'll fix this light. Sure enough, fixed it. How does that work? It's restarting things is magic. Or reboot this computer. It's a Linux computer. I have to reboot once in a while. How the heck does that work? Any thoughts? It's magic. It always works. It always works. But it's really important. How is it that we can somehow get things to work by like just rebooting them?
Remove the state.
Remove the state. That's exactly right. Something's screwed up. So you reset the state to a known quantity. And every device that's ever manufactured, this is that topic of survivability, has an extremely well-defined, well-tested initialization sequence. So when you plug that thing in, it comes up into a known state. If it didn't, you wouldn't buy it. Would you agree with that?
Yeah.
If your router didn't have a repeatable, predictable initialization sequence, would your company exist?
The button's really big, right?
Yeah, it's right in the front. Everyone knows this. So in Erlang world, the mindset is if something smells wrong, blow up. So it's really a matter of, it's a bit surprising that in order to build reliable systems, reliable software, you actually have a degree of unreliability or fault intolerance. Here's an example of a case expression where I'm going to match this result. If I is an integer, I'm going to convert it to a float. If it's already a float, I'm just going to return it. If I omit any other condition, this will crash. So it's another type of assertion. You're basically asserting to the program that logically, these are the only two logical possibilities of a result. If it's not, crash. Same thing down here. This is another type of fail-fast. So this is a very convenient and interesting semantic within Erlang, which is I'm going to pattern match on the first three items, and then I'm going to bind to whatever the rest is. Right? So rest will be whatever the sequence is past 001. If this sequence that's returned by read is not start with 001, this will be a bad match and it will crash. When I say it will crash, I mean the process that is executing this code, that's running this code, will crash. We go back to that system view. It's that black box. It's that one thing, right? That goes down. Now imagine you're on a network and you're reading something. You're reading something off of the network, and you get something that doesn't smell right. You crash. Rather than dealing with the problem because you know you're isolated, no one else is going to be affected. You're going to crash, get restarted. Well, you're going to reestablish a network connection at some point. Well, maybe that next connection will be okay, right? Or maybe you have a bug, but maybe it was just an anomaly. So you have this magical recovery capability. It's like somehow magically sensing that your network access point is completely screwed and having like a gnome back there going like this, you know, automatically restarting it. But it's spread out through your entire program. Completely and utterly changes your approach to programming. All right, so much so that I'm going to summarize in a really awesome build out of like arrows and stuff. You guys ready for this? This is all, by the way, this is all HTML and JavaScript and Ping. I know it's like super fancy with all this fancy graphics, but I'm not using Keynote, man. All right, process isolation. Now, I'm elaborating a little bit here. You can actually eliminate some of these things. Somebody's messing with me. I'm just trying to stop. It's probably work. I definitely don't want some of that. All right, so process isolation means no shared memory. In this case, right? You can isolate other resources, but for the most part, we're talking about memory. Okay, so if you don't share memory, the only way that you can possibly communicate is by passing messages back and forth. I think that's probably logically true. Right? So once you have this sort of message passing design, you have this mechanism for creating extreme independence. Now I have SOC there, that stands for separation of concerns. But one of the most useful and informative principles in engineering. Separating concerns. So you say, this thing does this, it does A. I'm going to focus on A, I'm going to think about A, I'm going to really understand it. This thing is only ever going to do A. Because I don't want it to do A and B. That's not a separation of concerns. A can be very high level, can be very low level, but it's always ever A, separation of concern. When you have a system of independent components, it allows you, it encourages you, it begs you, it insists, think about every little process, every little black dot on that screen as a separate concern. Now you can think about that as a service. What am I doing? What's its life cycle? What is its API? All these different things get focused in one particular area. Once you have separation of concerns, you have a very elegant system to recover from problems. Because what you're dealing with a separation of concern is you have logical isolation in your program. So you have this, the smaller the area of concern, the less impact it will have in an outage. If you have a database, this gigantic, ginormous thing, the database goes down, you can take your whole application down. But what if you just have a small area which is focused on, high performance key value stored for this particular thing? You've taken this big thing and you've focused it in a particular area. Now when that thing goes down, you're affecting less. So separation of concerns, this narrowing, this increasing isolation, makes your programs much more resilient to failure of any particular component. And there's math behind this, but I won't go into it. As a result of being recoverable, you don't have to think as much about error handling. You can sort of abandon this idea of even handling errors. You can just crash. If something doesn't feel right or look right, you can crash. Now, that's not always the right solution, but it often is the right solution. And as a default, it's a good solution. Because if you can automatically recover from something, great. If you can't, you identify that and you code around it. So you move toward this sort of this systematic improvement of the quality of your software. So this is really it. So can you tweak that somehow? Can you tweak that? No, just don't do that. Like arrows and stuff, and like try to do like an ASCII art. So this is really kind of the thing here. So I'm going to sum up. I'm going to take some a period of questions, and I'm going to actually get into some code. This code rocks. Much better than like preaching. Preaching is okay. Reliability features. That's the topic title. Reliability features of Erlang. So I had to have a slide in here that actually had this, so I can't be criticized for not talking about it. So process isolation, right? That is physically implemented, virtually physically, in the VM, in the Erlang VM. So the VM itself is actually built around process isolation. There are guarantees, there are designs, and it's not just like a library. There's some code out there that will take a large heap and manage it for you. You literally cannot get to the memory. There's no pointers, but you also cannot get to the memory of another process in Erlang. You can get to its state by way of message passing, but you cannot get to its memory. So it is truly isolated. There are guarantees around corruption beyond a particular process. So you have, as a result, this sort of fearlessness about errors. You can be very assertive in the way you approach your code. Process supervision allows you to detect a fault, detect a crash, and then restart it. But really the core features, and we can get into some other things, but I think, actually I don't know for other things, I think this pretty much summarizes it. And it's right in the heart of what we've been talking about. So all these principles of reliability, what I might call survivability of software, that things that help the software to run and do what you want it to do, help it get selected in favor of your opponents, who are always competing with opponents, and we want our code to get selected. I know that's not cool to talk about, but that's true. We want our code to live. But all of these things are explicitly supported in Erlang itself. So I think it's a unique language in that respect. It's a very architectural or very systems-oriented language. I think I'm going to demo to you that I do. So let me stop and just are there any questions or rants or objections?
Do you have a REST-like feature in Erlang the way this language does?
Have a what?
REST-like feature, because REST-like in Lisp, because in Lisp you can actually program the code that it will wait for instructions upon anything goes bad. So, for example, in the example with the tuple, if actually by some odd mistake you would pass error and an error, it would crash.
Okay.
But if you wouldn't want the process to crash, because you would want it to actually, be going on, sorry.
That's fine.
You can use another database in that case, for example.
You code it specifically for that. You handle that explicitly. So you would take that error condition, error condition, error count, whatever, and then you would deal with it however you saw fit. So there wouldn't be anything automatic or non-explicit. It would just be Erlang code that you would write to handle that. There's no language features that will kick in. At that point, if your process dies, it'll get an exit code, which can be tracked, just like an OS process. That's it. That's the only mechanism that's out there. So your supervisor, the supervisor mechanism in Erlang is very simple. It detects a process crash and then makes a decision, should I restart it or not? And there's some rules that it uses to decide whether it should restart it or not. If it decides to not restart it, it will in turn crash, may in turn crash, and which can then be percolated on the chain. So you can create hierarchies of sort of logic around restarting it. Yeah, so that's, I think, probably where you would approach that. Or you would be someone that, there's probably some very, you would code some intelligent ways of handling that. So an error condition in that case might be a very legitimate result that you explicitly
So
handle.
basically the signaling of errors is done by crashing the process and populating it on the chain.
There are exceptions in Erlang. Yeah, so you can actually throw an exception and catch an exception. You can also, of course, match against a pattern. Patterns are used by convention to signal errors, and those are the two ways. But at the end of the day, it's that process that's running or not. So the process. So if there's an unhandled exception, it will propagate up to the top. That exception will crash with the reason of that error, and then that can be handled by somebody else. Anything else that came up here? Does this resonate with anyone, or is it? My guess is that people who run systems probably can appreciate some of this. If you've written like iOS programs, which really probably don't have to have this. This is the wheelhouse for Erlang in this case. I think is server-side software. I mean, it's the wheelhouse. You could apply this elsewhere, but if you're writing long-running processes on the server and you have a discretion about your platform, I think Erlang is a really good choice for that for these reasons.
I want to add something about the handling of process there, and this is kind of different than other languages in Erlang, because the process that is handling error doesn't have to be the process who's using your process. So you can use a service and someone else is going to handle the error, all the errors. And the way the missing passing is, if you're expecting the process to give you feedback, you will have to send him your address. So anyone who's handling the error of the process can restart new process, and this new process can give you the feedback. So
This is most languages how it's done, but then when your supervisor starts, what then?
So supervisors can be supervised.
Yeah.
And then there's a top level service, which is part of the kernel. And depending on the type of application that you start, your application will stop. So Erlang applications are, Erlang runs the systems of applications. So it's sort of the unit of packaging is it's called an application. In other languages, you would probably call it a module. But the reason application is called application in Erlang is because you can start it. You can start it and stop it. When you start an application, all sorts of things pop up and start to run, including that top level supervisor. if the application is a permanent application, it'll get restarted. If it's temporary, it'll stop. It'll just die. So the application will just stop. So at some point, you need to start to monitor your applications if you're interested, and then of course you need to monitor your Erlang process also. Erlang doesn't bother dealing with out-of-memory conditions, crashes. The process, the OS process crashes. So it's a common way to lose an Erlang process is by running out of memory. It's easy to run out of memory. You just keep using it. Use it, and then you die. You have to supervise your Erlang process. Similarly, your node, the server itself, ought to be supervised. So you ought to have something monitoring. You have heartbeats coming out of the server, and then you also have an external monitor. So you generally have two ways of monitoring things. So you just start to cascade back up. And at some point, you leave Erlang world. But all the principles of reliability and fault tolerance and recovery apply, even outside of the Erlang VM. Okay, so I'm gonna get into an example here. So this should look very similar. I basically copied and pasted, changed some arrows around. But this is gonna be a system. And one of the questions that comes up a lot, when you're used to writing software in most languages deal with software through, I would say, kind of a stateful model, like MVC, like this model there. And then you've got the view, which gives you a UI to it, and then you've got the controller, which applies logic to it. But that model is kind of front and center. So it's like, well, how do you build a Ruby on Rails application? Well, let me talk to you about MVC. Well, how do you build an Erlang application? Well, let me talk to you about service orientation, or process orientation, or systems design, the things that we're talking about here. So this is an example of a very legitimate piece of software that's in the form of a system. So we're not talking about, there's no model here. Don't care about the state at all. I couldn't care less about the state. These are only services. We're talking about types of protocols and communicating with services. So if you're ever dealing with enterprise architecture jargon, anyone here like in the big enterprise space where we hear an enterprise or service-oriented architecture and so on? Anyone? It's a big deal. And it was a big deal like 15 years ago. And it's still a big deal. And it's a big deal because it freaking works. Service-oriented architecture works. Like successful projects do that. They follow separation concerns, isolation, they keep things small and focused, and they erect services, and the services interact within an enterprise environment. All we're doing is taking that same idea and applying it to a little tiny program here as a demo. So here we have a client, and the client is going to get a value. He's going to talk to a router. The router's job is to federate or to coordinate the request of a value across multiple servers. In this particular demo, we have 2 servers. I have injected, so I just described that. Some of these slides are for the sake of readers. So I have injected into the server something called the sickness. It's like a zombie thing. So it will get some type of sickness and it will misbehave. Right, so that's like a bubble. And we'll see how this thing works. So I'm actually getting into some code here. How many people are familiar with Java syntax? Wow. Down, demon, down. That was my schizophrenia. The demon voice comes up through my history. Erlang syntax. Familiar with it? Oh, great. So I don't have to explain this. I got like knocked because like I have a tutorial, 3-hour tutorial on how to like write Erlang applications. And people are criticizing me for not going into syntax. Well, come on now. It's pretty simple. All right, so I'm glad for that. So I'm not going to get into a lot of this stuff. So if you're having trouble parsing this, I'm going to describe it, but just stay high level with me. Don't get bogged down in every detail. This is high level stuff. Just think high level, try to understand what's going on. The client, this is the thing that's going to make the request. Start link. There's this idea of starting a process. Right? So you're not newing up. You're not like newing, you're not like allocating memory someplace. You're starting a process. So when you create something new, it's a process. There's a start language. So I'm going to start this, don't worry about link. Handle task is something that basically is a signal in this case to do the thing that you want to do. So in the case of client is I'm going to get a value. We'll look at what that means, and then I'm going to evaluate the result. This is incidentally a pattern I like to use in functional programming. Maybe you also. Just really terse, and functions do just maybe 1 or 2 things, and you use lots of small functions. So again, separation of concern. Get value is just going to call out to router get value in this case. So back to this model, right? Client, all he's going to do is go out to this. Now this, incidentally, is going to be a wrapper. This call here is a wrapper for a message passing and receive. But we actually never explicitly send and receive a message. It's just a wrapper that goes through a function. That happens under the covers, but we're only ever dealing with an API facade in this case. Okay, so I get the value, and then I'm sorry about the wrapping here. I evaluate the result. If it's good, I say, hey, this is great, I got this value. If it's error, I said, I'm unhappy, I got this crap, swears, terrible client, and rinse it. So it's very simple. And he's going to run every repeat interval, which I think is 2 seconds in this case. Questions about that? Super simple. This is simple. All right. The router is slightly more complicated. I have two slides for this. Again, start link is going to start the process. And there's a state initialization here because I'm maintaining state of the servers I'm interested in talking to. So the router in this case has 2 servers. So on configuration, he's going to get the server list passed and initialized state. So that's that whole thing when you restart your access point, you have a well-defined initialization startup. Same thing is reflected here. It's reflected exactly in the API, start and init. So when you think about this, you're saying, I'm going to start this thing, I'm going to initialize it. So if it crashes and it gets restarted, what happens? You initialize to that known state again. So initialization is an important part of this. Here it's going to, the router is going to go, this is a dispatch to the back end. I'm going to skip that. Just forget that a second. This is the workhorse of the get. He's going to try some servers, given the state. So the state contains the list of servers. He's going to try the servers, and he's going to get this result. Here's the reply, and here's the next state. So we don't exactly know what's going on. It's a little bit mysterious, but we know that it's going to try some servers, it's going to get a result, and it's going to have its next state. And then it replies with the reply, and then the next state. Erlang processes are single-threaded, so there's no global memory. You don't go poking things in global memory. So it's just a function. So here's my initial state, and here's my next state. Everything is explicitly right. So this should make every functional programmer here giddy with delight. The fact that you get a call here, that's my state, that's my next state. And there's no other, this code is the only code that is ever running in that process. There's no multiple things running. So you're single-threaded right here, and there's no global memory. You're getting passed in your state by the top level things is managing that for you. You mutate it in some way and pass it along. Very sort of pure in that sense. All right. This is kind of I-bleed code, but basically it's the implementation of the try servers algorithm. So we're basically going to try a server right here, get value. So this is the module function argument. So I'm going to try to get the value. If I get the response, that's great. I'm going to return it, and then I'm going to move to the next server because we're going to use a round robin. This is a router that goes round robin to the servers. Very simple. This server, the next server. Server 1, server 2, server 1, server 2. If it gets a value, it's great. If it gets an error, I don't really care about the error. I just want to go into the next server. This is very common. So Nginx behaves this way. So Nginx is a reverse proxy. It sits in front of app servers. Apache can be configured this way with different modules. So it basically tries a bunch of upstream servers. So if one of those upstream servers goes away, it'll just go to the next one. That's how you get availability in a web application. You have a very simple device that's fronting complex app servers. Those app servers can go away, and the router will handle the logic of failing over if one goes away. That's all that's going on here. So this is the implementation of next server and next. So this code, if you're interested, I can make it available. Incidentally, this is greatly abbreviated. I have the full source code. Finally, the server. Start link again. Start it up. Ignore that. That's the front end call. This is the workhorse here. This is the get. So it's going to generate some value. Don't know what that is. And it's going to reply. And here's a little thing, apply the sickness. So if the sickness occurs, then something bad is going to happen. So typically we would just apply the value, but we want to inject some sort of bug, right? We're going to simulate a failure. That's the whole point of the exercise. So we have this router, he's going to dispatch the servers. Sometimes the server is going to have the sickness. We'll see what terrible things result. Okay, so here's the sickness. If it's has the sickness, if that's true, exit I the sickness. Okay. It's a sample code, don't get upset. It doesn't actually have this, it's fine. All right, so here we go. that. So I'm just going to run this. So this is that code. So here we see this is 2-second intervals. This is live. This is actually happening. It's really exciting. So it's going back 1 and 2, and it's a 1 in 5 chance of having the sickness. So here's the sickness. So he replied from 1 and he went back to 1. Oh, look, 2 of them failed at the same time. Now he says, I'm unhappy I got this crap, no servers. But see, there's a supervisory thing going on here. So when somebody has a sickness, it's fine. He dies. Restart. Regeneration. It's like rebirth. No more sickness. So this is a really simple model. I can run this. I will run this. I'm going to leave this for my commitment to you. I'm going to let this thing run on my laptop for the entire time I'm in Poland. I will not, so I'll close it, it'll suspend, it'll stop for a while, I open it, it will resume. We'll see if this ever behaves differently from this. Be interesting, right? This is a very stable, survivable system. Like, some things get the sickness. You don't even know. It could be a coding error, it could be some sort of external variable that you didn't anticipate. But this is why this stuff is running in CloudBees. Because there are all sorts of errors that occur in production. But because of this whole system reliability, survival, the stuff I've been talking about, I don't get paged. It just restarts and recovers. And so we can keep going with this. And this model is a very realistic type of application where you've got unreliable data sources on the back end, you've got something that makes intelligent decisions about how to handle failure. Maybe everything fails, and so it propagates back up to the client, whatever. This is the way that I tend to build systems, because I like this a lot. I like the idea of building software that always runs, that survives. I like the idea of having my code always running, just out there, in the surface. Because I'm programmed to do that, right? I'm programmed to exist and to reproduce and to all these things. So it's just part of the evolutionary process. So that was the demo. We talked about that. I think this is more summary stuff, and again, this will be online, so people who can take a look at that. Let me make a point here, and I talk about Erlang a lot because it really is it's the only environment that I know that takes an operating system view to this. There's no reason you can't take an operating system view. Like, take an operating system and go run very small, focused programs, written in C, written in Python, written in Ruby, written in Java maybe. It's difficult when you have to start something up and you have 70 megabytes of resident RAM just to start the program. It's a little bizarre. But maybe, whatever. I'm bigoted and terrible. And we're a Java shop, so I should be really nice. But it bothers me that Java programs take up so much memory time. Let's say you write a really efficient Java program. Then you start it up, run it, you let all exceptions, screw it. Java's great. Use Java. Java, it doesn't matter how much memory. It doesn't matter. It'll take 20 more milliseconds. 20 more milliseconds to start up than something else. It's not that big a deal. It's fine. Use that. So let all exceptions propagate. Don't do any other hand. Just let your process crash. And then use something like like Runit or LaunchD or Systemd. There's all sorts of monitoring or supervisory frameworks that you can run on the operating system that will just restart with them. And then you communicate with other things over messaging. So sockets would be either raw TCP sockets or HTTP. ZeroMQ is a really, Peter Hitchens and the ZeroMQ community really understand this model of creating single-threaded, focused processes that are run in isolation, that don't share anything, that go through messages, and then ZeroMQ becomes the transport layer for that. It's a profoundly powerful model if you're not interested in just going wholesale into Erlang, and frankly, in some cases, you just can't get over Erlang. So that's my full disclosure that I'm not completely all Erlang all the time. So this will again be online, but I'm kind of pimping a couple of things here. The reason I have E2 project at the front is it's really the only kind of set of documentation that takes this message and mirrors it with actual code that you can go write. So I think from a I want to get started with Erlang. There's a good tutorial there that actually walks you through writing a socket-based key value store. It's very incremental, very iterative, very evolutionary. It takes this model of process orientation and service orientation. So if you're interested in actually taking this any further concretely with the language, I would suggest going to the E2 project site. I've written some things about this, so I have that, and honestly, Erlang.org is your best source. It'll get you everything you need, and not there, it'll point to things. So there's lots of good resources online. So with that, I'm done, and we can have questions. And if we don't have questions, we can have beer or both.
I can try Go.
I have looked at Go. I've not tried Go. I've actually been spending a lot of time with Julia. Yeah, no, I mean, until you have like guarantees across processes that one process can't corrupt another, I'm not that interested. Because really, that process isolation starts it all. If you don't have process isolation, none of this applies. It's gone. Forget about it. You have to, and to me, maybe it's a feel-good thing, but I don't want to have, when people talk about, there are some frameworks that provide this sort of virtual guarantee. Well, so did Windows 3.1. That's what it was, the whole design around it was to provide sort of a framework for you if you used it correctly. I don't care about using things correctly. I want guarantees. And this is the way, no one would put Windows 3.1 into a server production. Nobody. But why? Why would you do that? It'd be insane. But yet we're willing to go put a Java program into production, which has unbounded heat. Anyone can access anything they want. There's no isolation whatsoever. That's fine. We'll put that in production. Well, this doesn't make any sense to me. I want the guarantees. Anyone else?
You mentioned that you had a lot of stuff written in Python. When you learn Angular, you should try to move that philosophy of isolation, Python, or other languages.
I almost planted that question. That couldn't have been a better plan. So I've adopted a pattern of, there's a program called EarlPort. It's a library that basically exposes Python explicitly as single-threaded external processes that Erlang can talk to and treat as essentially a server. So one of those black boxes in the diagram, and it basically spins it up within, it's a separate process, but Erlang communicates with it over standard I/O. And so you can have access to all of the Python libraries, which are fantastic, and all of the REPL stuff and everything else that's good about Python you have access to, but you coordinate it through Erlang. And if there's a problem with that, it's a separate OS process that gets killed off, and then you can have that sort of pattern of just let everything crash. So you'll see system exit, or it's actually OS under exit. It's a more direct exit. Really aggressive process death with the slightest problem, or assertions or whatever else. So you can do that. EarlPort works with Ruby and Python, and I like to do something for Julia because I think Julia is has a huge future ahead of it.
You showed a slide about ZeroMQ, but earlier you mentioned Rabbit. Why do you stay with Rabbit?
So Rabbit, ZeroMQ is basically like sockets, but for messages. So rather than sending a byte stream, you send opaque messages that are delivered sort of however they get there in one chunk. They're written in one chunk and they're consumed in one chunk. So your unit of send and receive is the message. So it gives you it gives you basically the exact same semantics as a socket, but for messages. So it's very different from RabbitMQ. RabbitMQ is basically a full messaging server running a fairly complex protocol like MQP. So it's a hub and spoke model. So you have a broker and you have your clients, and it's very, very functional. It gives you a lot of things. The problem with it is that it's difficult to evolve it. The nice thing about ZeroMQ, very different approach, very different technology. They're not interchangeable. They work together. But ZeroMQ will allow you to take off a much smaller chunk, solve a little problem first, and then evolve that. Rabbit wants you kind of to live in that particular architecture. And the problem that we had is once that server gets saturated, there's two problems. Once it gets saturated, it's difficult to deal with. Second of all, it's a huge point of failure. It's difficult to federate it. So if you want, again, more isolation, separation in your higher level routers, Rabbit is difficult. ZeroMQ is very easy.
ZeroMQs.
What's that?
So you couple with ZeroMQs?
Yeah, we have a legacy RabbitMQ, but ZeroMQ is sort of the future. But the legacy is probably going to run forever. But as we add new things, it's added through ZeroMQ because ZeroMQ will let you do like really specific things, and it just follows that. So it's like, oh, I've got a big load over here, a big hotspot. I'm just going to take this traffic and funnel it down over here, and provide a little point solution for that. And I like ZeroMQ because it's just Peter and that community understand this very well, and they're focused on it. They're doing a great job. solving this problem. Thank you very much. That concludes it. Is it really 8? So I'm an hour early. Well, that makes sense. I mean, I usually have like 40 minutes left, so I'm an hour. So we have time for something. So I would say this. I would say what I tend to do in this case is, so I organize the Erlang user group in Chicago. So sometimes this is incidentally a huge turnout. It's really humbling. We need to have half this. Anyone who wants to go or needs to go, please feel free at this point. I think we can maybe call this done, but I'd like to use the time for something interesting. It could be early, it could be something else. I'm kind of open if people are interested in learning more, diving into specifics about Erlang at all. If you are functional wonks and want to know something about something there, whatever, we can try something on that front or something else. Ideas?
There's still some pizza.
There's still some pizza. So we could do an informal, yeah, we can break, I don't know what. Ideas here, brainstorm, spitball. Thoughts? Because I know we have a reservation at 9 for beer, for bar beer, which is different from this beer. It's still beer, but it's like in a different context. And that's at 9, so that's like 55 minutes from now. So it's kind of a problem. It's not a problem.
Do we have to wait till 9 to go to?
We might have to. Yeah. But I don't want to give up on this idea. Like, it could be maybe like there's like 3 people who really, and then like if you just one person said something small, like 10 people would be, and then we just have like this wave of enthusiasm for an idea. You never know.
Okay, so let me try. We have this isolation. Something dies. What if it doesn't come up?
That's a good question. I would describe that as yeah, that happens. That's a fundamental problem. So here's a scenario I can give you that fits into that pattern. So let's say you're connecting to a database. Typically, in a process, you would try to connect to the database. What happens if you can't connect to the database? Well, it would typically be an error, and then that process would die. And then you get into this like really fast loop. Like you could just say pounding this server quickly. Erlang has sort of has a release valve that lets you stop that. It says if you restart so many times within so many seconds, stop trying. But that's no good either because you want to connect to the database. Let's say the database is down for 15 minutes. Who cares? Like I just want to connect to it. What I'll do in that case is I will do one of 2 things. I'll either add the logic, I'll start the process, and I'll send a message to itself to try to connect. It'll try to connect. If it fails, it'll send a message to itself again. So that process will basically always live, and it'll always be trying to connect. Or if it's a particularly complex operation, I'll move that initialization into another process. So I'll spawn another process. They'll say this process is designed. It specializes in establishing a connection. So maybe it might have some extra special logic, etc. So he gets the connection and passes it over to this guy. So it can get very complex. But what I like about it, Erlang, is that it gives you the semantics and the feature set to sort of think through what you want to do. But it's a very common scenario to have a restart, especially on an external dependency that's unreliable, be a network service or whatever. You want that process to be alive. That process could be fronting that back end. Say, if he's down, I'm going to give some sort of meaningful response. I'll cache some values, or I'll say down for the time being, or whatever. So it sort of comes down to how robust and clever you want to build your service levels, I would say. Does that get to your question?
Yeah, I guess.
There's nothing magic about it. That's one thing. There's no magic to Erlang at all. So it's like you run into these problems. It's like, okay, this is an actual problem. I've got to kind of think about how to. There's no like auto map. It's really dumb. But
That's what it works.
those are the best things. Dumb's good. Chisels are good.
It's actually the most impressive problem, you know, it's
So the question was, what's the most impressive piece of code written in Erlang that I've seen? I tend to personally appreciate the code that is, I like to think of, again, the survivability thing often translates to me into really, really good abstractions. So solving a right problem, and that is often a very simple solution. But because it's such an important problem, like, so I would say, probably the most impressive code for me is some really simple code written by Ulf Eiger called gprod. It's a registry. It does different things. It can be used for different things. The thing I like about it is that in Erlang, processes want to be black boxes. So you want to not know anything about the less you know. It's that independence or isolation thing. The less you know about something, the better. So you start it, and ideally you forget about it in a year. So that's the ideal system. Is like something there's no dependencies. You just start it and fire and forget. And then you can incrementally get more and more interested in state and protocol. But in a lot of cases, you want to broadcast statistics about like how fast is something going, or what's my current state, or what's. So how do you do that? You don't want to reach into that black box because it's expensive and it's invasive. What you want to do, this is the way that most, like MySQL or Postgres, this is the way they work. They constantly broadcast state out to some place that we can then query. So rather than invading the process space of MySQL, say, give me the stat. You never touch that. You only read what it wrote out to someone, and then it can write that at its own discretion. gprod was that for Erlang. So it lets you publish statistics or other status information. So let's say you're dealing with processes that represent users in a system. There's nothing about a process there's no like user process. It's just a process, and it has a state, and you can't see the state. So you have no idea what kind of process it is. Let's say you want to enumerate all of your user processes. There's no good way of doing that in Erlang. So Ulf's library, gprod, will let you say, when I start this up, register my process as a user process. And you can say the user ID is this. You can do other things as well, and then kind of query that. So you're getting into sort of complex systems. It's so important. It should be part of the core. So that was very impressive to me. And there's a great PDF, there's a great white paper written on it, the reasons about this, and sort of more lofty context with it. There's a lot of engineering effort that goes in. There's a lot of like hardcore. I'm like a convert. I'm not a thought leader. I can sort of understand what's going on and hopefully make good use of it. There's a lot of amazing thought leaders and engineers that tap into. There's a good reason all this stuff works. Not because like they got lucky. I think they're just tenacious, and that's one of those libraries I think that fits into that category. It's simple. It's a very simple library. It's not sophisticated about it. All right. So I think that my interpretation is that the general inclination is to mill about until something else happens. That would be my read here. This could be so I'll stop and let our state evolve naturally. There's probably some beer left. We'll go to the bar. We'll just go early. Can we just go early?